So it is a pleasure to have Kazunobu Maruyoshi from Seikei University. He has been visiting here for 1 month or so, and but unfortunately he is about to leave in a couple of days. And so before he leaves, we asked him to give a seminar, which will be about the dualities of adjoint SQCD and supersymmetry enhancement. So please.
Okay, thank you very much for coming, and it's a great pleasure to coming back here. And I'm come from Seikei University in Japan, especially in Tokyo. And maybe if you consider to visit Japan, let's meet in Tokyo if you are interested in. And so my talk is about the four-dimensional supersymmetric gauge theory and related to the superconformal field theory. And I talk about some dualities and also the enhancement of supersymmetry. And this talk is based on the collaboration with Emily Nardoni, who is in IPMU, and Jaewon Song in KAIST in South Korea, and also this paper. So I'm not sure whether you are familiar with this kind of topic. This will be very basic introduction. So if you are expert, maybe you are boring, but let's start. So in standard QFT, if you start learning the QFT, you start from a bare Lagrangian or some UV theory, and study what is quantum correction, or what is correlation functions, or scattering amplitude, etc. Let us consider a four-dimensional SUN gauge theory with some quarks. This can be seen as follows. Suppose we have some free fermions, which we denote by T free, with an SUN global symmetry. Maybe let's say we have n free fermions. This has SUN global symmetry. Then we gauge this global symmetry by adding SUN vector fields or coupling to SUN vector fields. So by this, we can get SUN gauge theory with some quarks. The quark corresponds to this fermion. So pictorially, this can be this kind of thing can be considered as follows. So here T free is a fermion, and this has global symmetry SUN. So this box corresponds to the global symmetry, and then we gauge this SUN global symmetry by gauging. I change pictorially to the circle. Then this denotes the SUN gauge theory coupled to these fermions. Okay, so I think this is clear. And what we have to do by gauging is done by adding this coupling term to the Lagrangian, where J is the current, conserved current associated to SUN global symmetry of this T-free part. This is totally clear, I guess. But it is, and this is standard, but it is perfectly okay to consider different matter sector, which is not free. In the previous transparency, I used the free sector, free field, but it's okay to couple, or it's okay to gauge not free theory, which is conformal field theories. So now let's have a CFT, which is denoted by T CFT, with some SUN global symmetry. And then we gauge the global symmetry of T CFT by adding SUN vector field. So pictorially, this can be denoted by this gauge, by this form. Okay, this is nobody stopped us to study this kind of thing. And the gauging is done by adding to the Lagrangian this coupling term. Again, this J mu is the conserved current associated to SUN symmetry. So TCFT should have this kind of conserved current because we say that this has SUN global symmetry. So however, this is to study this kind of theory is difficult because the main difficulty comes from CFT cannot be written in terms of free fields. This is this might be a strongly coupled conformal field theory, and one cannot use the standard technique of the QFT to study the theory, maybe perturbation theory or something. So there is this kind of difficulty. However, if the theory is superconformal field theory, something we can do, or many things we can do. So just change TCFT to TSCFT with SUN global symmetry. Then this picture is the same. Then we get SUN gauge theory, or if we want to keep the supersymmetry, this is n equal 1 gauge theory, SUN gauge theory, coupled to some superconformal field theory. So the matter sector is changed to this superconformal field theory. So in this case, again, the coupling term is written in terms of the superfield formalism, like this. This is the case for n equal 1 superspace formalism. Then in this case, we knew a few properties of superconformal field theory. For example, central charges, a superconformal index, some partition functions, etc. So we can learn something for this gauge theory. So a remarkable example of superconformal field theory is n equal 2 Argyres-Douglas theory and its generalization. So so we use as a matter sector, we use n equal 2 Argyres-Douglas theory. However, we can gauge this global symmetry by n equal 1 vector multiplet, or you can do n equal 2 gauging. It's up to you. Today, I will focus on this kind of superconformal field theory, or more precisely Argyres-Douglas theory, and which is called as DPSUN theory. So I will explain later what is DPSUN theory, but let's say this is some superconformal field theory with SUN global symmetry. So then I can gauge the SUN global symmetry of DPSUN theory. Then we get SUN vector multiplet, SUN gauge theory coupled to DPSUN. And also we can add some free part. This is the chiral n equal 1 chiral pair of the chiral multiplet. So NF pairs of fundamental and anti-fundamental chiral multiplets. So by this, we can get some SUN gauge theory coupled to T-free part and also DPSUN theory. So, so there is a two-line explanation of DPSUN theory, which is n equal to SCFT of Argyres-Douglas type with the Coulomb branch operators with fractional dimensions. This is the kind of definition of Argyres-Douglas theory, but I will explain later what is DPSUN theory more. This is first named by Cecotti del Zotto and Cecotti del Zotto Giacomelli, Italian guys. So we have studied this kind of theory, and when we for a particular number of NF, P, and N, which is the typical integers coming from specifying this theory, and one can check that the gauge theory flows to the strongly coupled fixed point in the IR, in the infrared limit. So we focus on this kind of this kind of fixed point, which is SCFT, in the following. So then we see that this theory shares the same fixed point with another 4D theory, which can be written in terms of the free matters. It means that there is no strongly coupled sector. So, okay, so before going to that, what is duality? The duality is in the Seiberg sense. So two different looking theory is flowing to the same fixed one, same IR fixed point. For this, we say A theory and B theory are dual to each other in the Seiberg sense. So then what we found, or what we propose, is the previous n equal 1 SUN SQCD coupled to DP SUN theory, with furthermore deformed by this superpotential U0. I will explain later, but this is the lowest dimension Coulomb branch operator of this DP SUN theory. So by deforming this theory flowing to the IR fixed point, and this is dual to the SUN, again, the SUN SQCD, the number n are the same. And with a joint chiral multiplet phi in the adjoint representation of this SUN with superpotential trace phi to the p plus 1. Here, p is the same as this p. Maybe pictorially, this theory in the quiver diagram, like adjoint fields can be is written in terms of this. Yes.
So, but you have a mass for this adjoint diagram, or just this superpotential?
We don't have it. We can tune this p to 1, but this is not. We don't include this case.
So
yeah.
If you don't put that W, that would be an equal to. Or no?
Not because if.
No, because there is always the fundamental.
No. Matter content itself is the n equal 2, but we don't have a coupling between phi and quarks. Yeah. So it's not n equal 2, but n equal 1. But we will discuss this kind of thing later. Okay, so this is our proposal. Some theory with strongly coupled sector is dual to totally Lagrangian theory. And yes, then so if you are a relatively senior person, maybe you are familiar with this right hand side. This was already studied so far by Ktasov and collaborators, maybe Ktasov and Ktasov-Schwimmer, maybe famous as Ktasov duality or something. And yeah, this theory has another dual description, which was found by more than 30 years ago, which is n equal 1 SU p times nf minus n adjoint SQCD with nf flavors and many singlets with this superpotential term. So what we have found is the kind of third dual description of this Ktasov type theory with adjoint. Okay, so this is kind of a very vague explanation of my presentation. So I will go into the more detailed part from now on. So, but if you have any question, please ask me at this point. Is clear? Maybe yes. Okay, so let's start from explain what's the DP-SUN theory. So this naming comes from these guys. We have many different namings of Argyres-Douglas theory, and this is very confusing thing. I will later discuss about this naming, but okay, let's say what's the DP-SUN theory. So this is n equal to SCFT superconformal field theory of Argyres-Douglas type with SU2R times U1R symmetry. if this is n equal to SCFT, there should be SU2 times U1R symmetry. So then flavor symmetry is SUN if n and p are coprime. So we choose this case. And if this n and p are not coprime, the flavor symmetry is SUN times some U1 extra factor. And we don't discuss this case. Let's focus on this case. So then the flavor symmetry is just SUN. So, so the global, Coulomb branch is spanned by the Coulomb branch operators, whose dimensions are given by this form. This is fractional, generally, and then n comes from this n, and p comes from this p, and j is run from 1 to n minus 1, and s runs from 1 to p minus 1. Okay, so then there are ADE group generalization of DPG theory. SUN will be changed to SO and E-type thing. So then this is the Coulomb branch. But the Higgs branch also interesting. Okay, so if the theory is n equal to, there is Coulomb branch and Higgs branch. Then the Higgs branch part is something like this. The Higgs branch of this theory is identified with the principal nilpotent orbit of an minus 1 algebra, where n is the same n. Then the associated to vertex operator algebra is SUN Katsumuri with this level. And this was found by Danxi and collaborators, and also Arakawa, and some years ago. And it means that the vacuum character of this VOA is identified with Schur index of this DP SUN theory. Then also there are some relation in the operators. For example, since this has SUN global symmetry, there are moment map operator mu, which is the lowest component of the conserved current multiplet. And this mu satisfy mu to the p of adjoint part is equal to 0, and also trace of mu to the k is equal to 0, where k is any integer, 1, 2, 3, 4, 5, any integer. So mu satisfy this kind of operator relation, and these are checked from the study of the superconformal index, and this is important for duality works. Yeah. Okay. So then about the naming. So DP-SUN theory, this has SUN global symmetry. And okay, so let's say n equals to 2. This is DP-SU2 theory. So this is equal to A1 DP theory, which you guys are familiar with. And then this A1 DP theory is a maximal singular point on the Coulomb branch of the SO2P pure super-Yamil theory, or SUP minus 1 with two flavors, where mutually non-local massless particle appears. And also another notation by Danxi and collaborators is in the another notations, DP-SUN is equal to JBK comma F theory. So where J is equal to n minus 1, and K is equal to P minus 1, and B equals to N. So this relation make okay, so okay, so this may be clear if I go to the next slide. F corresponds to the F means the full, and this corresponds to full puncture in the class S. And yeah, this is a kind of much associated with class S picture of this SFT, which is like this. There is a class S realization of this SCFT, which is maybe you are familiar with 60 n equal 2 comma 0 n minus 1 theory on a sphere with regular maximal puncture, this one, and irregular puncture of type this one. This is two punctured sphere. One is regular and one is irregular. And F means in the previous slide correspond to this regular puncture. And this regular puncture carries SUN global symmetry. So, okay, so this has the kind of brane or M theory construction. So maybe we can study the our theory, our gauge theory from the brane M theory perspective, but we haven't think of it yet. Okay, so this is the kind of explanation of DP-SUN theory. Again, we don't have any, sometimes we have some Lagrangian theory which flowing down to this kind of superconformal fixed point, but we don't know at all what is this theory. But still we can compute some variable. For example, there is a flavor central, so-called flavor central charge, which is given by this value. By the way, the flavor central charge is computed by this from these anomalies. So it means that we knew the anomaly, trace R times TATB, where TATB are the generators of SUN global symmetry. And R correspond to the U1R. So then also we knew the central charges of DP-SUN theory. This A and C are this value. Maybe this value, these are computed in this paper already. Okay, so by this the kind of explanation, and then we will gauge this global symmetry of DP-SUN theory, and then we get the SUN theory coupled to DP-SUN theory. But before going to that, let's see this slide and some few slides more will be almost explain what we are going to say. So which is the following. So let's just the DP-SUN theory. Then let's do some n equal 1 preserving deformation of this DP-SUN by adding W equals to U0 term, where U0 is the lowest dimension Coulomb branch operator of this DP-SUN theory. So I explained that there's a Coulomb branch operators with dimension like this. The lowest dimension one is with dimension p plus 1 over p. So and then let's deform by this operator by adding superpotential. So this is just n equal 1 preserving. So n equal 2 will be broken to n equal 1. Then in order to study this, we have to be careful about what is the low energy or IR R symmetry. Then this R symmetry should be the combination of the U1 symmetry in the UB. I mean, UB means the DP-SUN. So the DP-SUN has R symmetry, R, and also the big R, where this capital R is the Cartan part of SU2R. So there are two combinations, R0 and F. This R0 is a R symmetry type combination, and F is the kind of non-R global symmetry, this one. So then the IR R symmetry should be a combination of this R0 plus epsilon times F. F is this one. Then, so epsilon is unknown coefficient, which will be fixed later, which will be fixed soon. then this should be the combination. This should be the IRR symmetry. Fortunately, in this case, it is very easy to fix this epsilon because the superpotential term in the IR should have charge 2. This is the some restriction coming from n equal 1 supersymmetry, and this determines epsilon to be this value, and this leads to the central charges, this one. So we start from n equal 2 dp-SUN theory deformed by U0, and in the IR we get in the IR R symmetry will be changed, then we get this central charges. And if you are very excellent student, you soon find that what is this? So this is a multiple of n squared minus 1. It seems adjoint. And if you calculate this one, this is you can soon find that these are identical to those of n squared minus 1, n equal 1 chiral multiplets with R charge 2 over p plus 1. So yeah, so this is what we can do by calculation, even without Mathematica. Then so what this is saying that this is adjoint, right? N squared minus 1 is adjoint. Number of the adjoint, number of the degree of freedom of adjoint, representation of SUN, and n minus 1 chiral multiplet. But R charges are somehow strange, 2 over p plus 1. But this means that somehow this is saying that we have a kind of superpotential, trace phi to the p plus 1. If we have this kind of superpotential, R charge will be 2 over p plus 1. So this is somehow saying that this dp-SUN theory deformed by U0 somehow related to the adjoint field with some such kind of superpotential term. So the special case is p equals to 2. If p equals to 2, this is 2/3. So this is the value of free field. So this becomes free theory. So so in this case, somehow it's okay to, how can I say? If p is not equal to 2, this flow, something like it's not good flow because the R charge will be something different from the free value. But if p equals to 2, the flow will be is good, and IR theory is a free theory, and this fact was already used in these people to find the remarkable duality, which is n equal 1 SUN gauge theory coupled to 3 dp-SUN theories, which are dual to n equal 4 SUN super Yang-Mills. So this was already found by these people. Okay, so this is one of the clue that dp-SUN theory with some deformation is equal to the adjoint chiral multiplet. Sorry, it's not equal, but somehow related. And another relation comes from by looking at the superconformal index of this dp-SUN theory. The superconformal index, if you are familiar with, is a kind of Witten index with some fugacities coming from some isometry of the geometry and also the R symmetry. This is R is a U1R. This capital R is a SU2R. And also there is a fugacity of the global symmetry. Okay, so this is a kind of Witten index. So then there is a Schur index, which is the limit that it is obtained by by setting Q equals to T here. In this limit, it is known that there is no P, that P dependence disappears, and we get just a function we get a Schur index, which is a function of only Q and also the fugacity of the flavor symmetry. So, okay, let's look at this Schur index of DP-SUN theory. And it is known that this is simply in this form. This chi adjoint is a character of the adjoint representation. And PE is a precestic exponential defined by this. So this is something like this. And again, if you are familiar with the superconformal index, you may soon see that this is similar to the superconformal index of the chiral n=1 chiral multiplet, which is this one, with R charge R. This is kind of similar, but there is here there is one parameter with flavor fugacity, but here there are two parameters, P and Q, and also flavor fugacity. So then, if I set P is equal to Q to the P, I use same P, but if we set like this and also R charge to 2 over P plus 1, these expressions are the same. So again, this explains that adjoint representation n=1 chiral multiplet with R charge, this value is somehow related to the DP-SUN theory. So this is another clue that our duality works. Any questions so far? Is clear? Okay, now let's couple let's consider n=1 gauge theory coupled to DP-SUN theory and consider their duality. So pictorially again, what we are considering is this in this picture. So SUN gauge n=1 SUN vector multiplet, which coupled to DP-SUN theory, and also NF pairs of the fundamental and anti-fundamental chiral multiplet, which I will denote by Q and Q twiddle. So then, so we now want to consider what's the IR theory, what is IR fixed point, what is the conformal window. It depends on this NF, the value of NF and P and also N. So, and if there is no this kind of strongly coupled theory, this is simply the Seiberg's SQCD. And depending on this NF, so the phases will be different. At some phase, supersymmetry is broken. At some number of NF, the confinement happens. And between some value to some value, the theory flow into the conformal. And more than NF is very large, the theory is IR free. So this kind of similar thing should be happen in this case. So then we want to know what is the conformal window, what is the case, what is the number of NF, which the IR theory is the conformal. So the first we can study is the one loop beta function. This is easily calculated in this case because we knew the flavor central charge of this SCFT. So this will gives you this value, one loop beta function. So we want to specify the theory to be this is asymptotically free. So it means that B1 loop should be positive. So this gives you the upper bound, this one, to n plus p, n over p. So this is upper bound of NF, which the theory is conformal. And also we can check we can check the lower bound of NF, the number of flavors of the conformal window. But this is not easy to write down in a simple form. this is kind of case by case. For some number of n, nf should be something or something. So I cannot write down this easily, but there is, we have worked out this f minimal or lower bound of this nf. This is not unrelated. So, okay, so this is a case-by-case study. For example, if the gauge group is SU2, P equals to 3, and F equals to 2, we get some IR fixed point. And dimension at the IR fixed point of U0 is 2.29 or something, or some another examples. So here we have not yet deformed by this U0. Just consider the gauge theory coupled to SU and vector multiplet. So then if the dimension of this U0 less than 3, this is relevant deformation. So we can deform this theory by adding this U0. This is what we will do now. Finally, we deform the gauge theory by adding this superpotential term. So by this, we get the, yes.
So those numbers, you wrote them numerically, so they're only known numerically, they're no like analytic expression?
I cannot, there is no analytic expression, unfortunately.
But there's solutions of some transcendental operations, or?
Yeah. Yes, that is true, but there is some algebraic equation, yes. There is yes. However, there one subtlety comes in because so if I try to work out, we have to do a maximize. We use a maximization, and this is simply the equation is a kind of quadratic equation, cubic equation. We have to solve the cubic equation, and then we can find the solution. However, some cases we have some. We found that some operator will be decoupled because if you do the A maximization, in some case we found that some chiral operator, the dimension of some chiral operator will be less than 1. So in this case, we have to subtract this contribution and we have to do A maximize again. Then again. Then once we get the good theory, this is the answer. So we have to do this process. So this is very complicated, and by this we cannot write down the simple form or analytic form of this number of flavors. So this is the reason why I cannot write this value. So it depends. So this decouple thing depends on the N and P and NF. So yeah, we don't know what's the simple form writing down when there are decoupled chiral multiplets, decoupled operators. So but if case by case we can study. Yeah. So then okay, let's continue. Then we can deform by this U0 if U0 are relevant. Then the fixed point after the deformation is easily computed again. Then central charges are like this, and the operator list of operators are something like this. Then what's this? And also this is our charge in the IR fixed point. So now so this is a list of operators, but so let's see what is this list. So here UI comes from DP, mother DP SEN theory. However, U0 are already used in this deformation, so there are no sorry, I should erase this 0. So there is no I equals to 0. But 1 to p minus 1, there are ui field operators. And also there is a bi, which is the kind of n equal 2 counterpart of this u. Because if the theory has n equal 2 supersymmetry, then if theory has Coulomb branch, then there is a Coulomb branch operator. However, if you have n equal 2 supersymmetry, this you can act the supercharge by twice. So then we get scalar component. So this is this B. So this also comes, this will be also the n equal 1 operator, chiral operator in the IR. So the dimension will be, R charge will be this value. So then we can have some mesonic type operator, which is q times mu to the j minus 1 and q twiddle, where mu is the moment map operator, which is adjoint of SUN global symmetry. So, however, there is dp SUN chiral ring relation, which I explain this one. So if mu to the p is equal to 0, so it means that this product should be only p minus 1. P minus 1. So more than that, chiral ring, there is chiral ring relation, and it's not independent chiral operators. So let's say this is MJ. Then also there is no trace of mu to the k something operator because of the chiral ring relation. And this is, I didn't write down the expression, but this is the baryonic type operator coming from this Q and Q twiddle. Okay, so then this is the independent operators in the IR, and this should be compared to the adjoint SQCD. So now we saw that this theory deformed by U0 will fix to some IR fixed point. And we'll say that this theory, n equal 1 adjoint SQCD with same number of flavors, will flow into the same fixed point. So so this should be quick because because the thing is not so new, the same computation what Kutashov and the collaborators did. And however, there is again the subtlety coming from the decoupled operators. So people are not so much worked out this kind of issue. And we try to work on these things, but unfortunately we couldn't find the paper working comprehensively the decoupled operator. What is decoupled operator or not? And we did the computation again, then we found what's the decoupled operator, and we tried to match what's the remaining operators between this adjoint SQCD and the DPN theory. So in the original side, we have a gauge invariant operator. Sorry, this should be Q, capital Q, sorry. Q mu to the j, Q twiddle, and this is mapped to. Okay. So this is mapped to this operator. This is quite similar, and this phi is the adjoint in the dual side, and also there is the operator which is U, and also this. Sorry, I should change. This is V, which I wrote. This is equals to trace to phi to the k operator. So there are operator matching between two theories, and this is kind of complete operator perfectly matched. Then we can consider matching of superconformal index. in general, we don't know the full index, full superconformal index of DP-SUN theory. So the check of duality in the full sense is difficult. However, we knew okay, so some cases we knew, for example, DP-SU2 case, we knew the index, and we performed the check for this, and this does work. So it's okay. Maybe this duality is true. And yeah, so then another reason is that the central charges are the same as adjoint SQCD. So maybe I'm not sure, but it's quite rare that the two different SCFT share the same central charges. So I guess once we get the same central charges, it means that it gives you the same IR fixed point. This is still the guess level, but yeah, maybe this duality Duality is true. Okay, I haven't tried, but no, yeah.
I don't know if it's
not sure. Not sure. Maybe for, I guess some theory can be, some index, twisted index of some Argyres-Douglas theory are known, but I'm not sure about this kind of thing. Maybe we can discuss later. So yeah, but I don't know much about that. And finally, this is the final slide. So as maybe Alessandro say in the beginning, some case the theory is n equal to 2. So we tune or we pick p equals to 2 case, and also the number of flavor is 2n. So we propose that in this case, with further deformed by this superpotential, we already deformed by U0 and also Q mu Q twiddle term. By deforming by this term, we expect the supersymmetry is enhanced in the IR. We start from n equal 1, but in the IR, the supersymmetry is n equal 2. This is our proposal. It is kind of easily see that central charges of this case is this one, and this is the central charge of n equal to SUN with NF equals to 2n SQCD. And also, this is if you compute the dimension of this U and V field, it is simply 2, 3, 4, 5, 6, n. So this is kind of the dimension of the operator, which is trace of phi to the k. So then this is the kind of operator dimensions of n equal to SQCD again. And also this enhancement is quite natural from the dual side, which means that in the dual side is adjoint SQCD. So matter content is adjoint, n equal 1 adjoint, and n equal 1 pair of the chiral multiplets. So it's the matter content is those of n equal to SQCD. And also this term is mapped to QX Q twiddle term, which is Yukawa type superpotential, which is should be there if n equal to supersymmetry. So, however, there is this U0 term. This is mapped to trace X cube term. But if I compute at the fixed point this dimension of this one, and it turns out that this trace X, the dimension or this operator is marginally irrelevant. So it means that this we don't care about this operator in the IR. So it means that this there is no kind of effect of these operators then flowing to this n equal to SQCD with this Yukawa type superpotential. So maybe I'm not sure of it. This is not a proof, but maybe convincing that therefore the fixed point has n equal to supersymmetry. So okay, so some cases with p equals to 2 and then f equals to 2n with some superpotential, the theory has n equal to supersymmetry in the IR. Okay, so the conclusion. So we found the dual description of n equal 1 SQCD, adjoint SQCD with NF flavors, and also the superpotential trace-phi to the p plus 1, which is the Kutasoff type. And this is the dual theory is n equal 1 SQCD coupled to DP-SUN theory. So, okay, so there can be a generalization of this duality by coupling, for example, more DP-SUN theory. For example, we can couple 2D DP-SUN theory. Then we see what the duality means. So, however, however, this and then adjoint SQCD side there is ADE type classification found by maybe interrogator and collaborators, maybe interrogator and Wecht. So then they consider the generalization of adjoint SQCD with two adjoints. So then they try to figure out what's the generalization, and they find out. They find. Okay, I don't need the slide. Then find what's the superpotential of two adjoints, and we try to find out the dual description to that two adjoint theory, but there's some problem coming from the chiral operator, and we couldn't find the generalization of this one. And also we can change to the different side, namely to change this SUN to the D type and E type. So for this, the duality should work, and we have considered this one, but really just a matter of changing the equations, and there are no new interesting things. So we didn't write down the papers, but it is possible to generalize. And also, as I said before, there is a M-theory realization of DP-SUN theory. So this gauge theory can also be realized in the M-theory framework. The difficult thing is the U0 deformation. So this is kind of technical to induce from the M-theory point of view, but maybe it's possible to consider. So, okay, so I stop here. Thank you very much for listening.
Are there more questions? Please.
I want to ask, there is an equivalent between S2 and F equals 4 and equals to gauge theory and equals to 2 star. So my question is, can this example somehow be fit in your picture, or it's completely different?
It's completely different at least in my picture. But yeah, I knew that there's some equivalence between n equal to star and n equals to 4. Yeah, from this picture, I don't know how to explain this kind of relevance. Yeah.
Can you show this picture of these two figures?
This one, the last.
No, this duality. Yeah, it is.
Mm-hmm.
So if I look at this, so it looks like we can start with the different series. On the left, we have Argyres-Douglas here, on the right, we have just some joins,
All right.
some multiplets, and then you do this procedure, you gauge symmetry, and well, you also couple to this some pre-center. And then, like after you, so it looks like you do some operation where you start with different series, and you get the equivalent series.
Yeah.
So you can forget some information. Is there a kind of intuitive way to understand why this happens?
So this okay. So one explanation is that it's kind of
because like you see like the left part of this, the central and the left part are the same.
yeah, that's true. So almost the theory is almost like this part is changed to this adjoint part. So and then it says that this DPSUN theory looks like the adjoint n equal 1 adjoint chiral multiplet. So the relevance of this DPSUN and the adjoint field can be seen, as I said in the beginning, but from this deformation thing, or from the superconformal index. This study is just by start from DPSUN deformed by U0. Sorry, this one. So then we just get this value, which is the central charge of n. This is adjoint times n equal 1 chiral multiplet with R charge, this one. So it strongly says that the DPSUN theory deformed by U0 gives you the n square minus 1, n equal 1 chiral multiplet. However, this is not but this is not good RG flow, because in the IR, what is this? So this value is not a good value, right? For the free chiral field. So if P equals to not equals to 2, this is not good field. So, but once you gauge the flavor symmetry, then the RG flow will be good. So by gauging is a way to cure this kind of wrong RG flow, and then to get the duality. Yeah, so this is a nice point. Thank you very much for asking.
Maybe I have a naive question. Is there maybe a geometrical framework to derive or at least understand this duality?
Maybe yes. Yeah. So this is what we have worked out: n equal 1 geometry. Yeah. So DPSUN is the sphere with one maximal and one irregular puncture theory, and the gauging is n equal 1. So maybe, for example, if this NF equals to n, this is just a 3 punctured sphere. So let's say we have 2 punctured sphere and 3 punctured sphere with 2 maximal and 1 minimal, and then glue the maximal punctures in the n equal 1 way. So by this, we can get n equal 1 gauge theory coupled to this one and n flavors. So however, this deformation is kind of a little bit difficult to realize. This, we don't know what's the geometric meaning. Maybe there is, but I don't know. We can find this is the geometric representation of this adjoint SQCD. So that will be interesting. Yeah.
More questions? So if not, we thank